Okay, guys. Hello. I hope that all of you are healthy and well. As you know, we have to start with online lecturing for a while because of the conditions that we are in. The first lecture that we have for today, which is actually the seventh lecture of this semester, is about complexation. Um, Complexation is a simple idea. You have two things. They combine together to make a complex. Or if we define it, complexes are compounds that result from a donor-acceptor mechanism between two or more chemical species. Generally the forces that are involved with complexation reactions are van der Waals forces, hydrogen bonds, coordinate covalent bonds, which we talk about this one in a while, after a while, charge transfer bonds or forces, and hydrophobic interactions. These are the most common types of forces that are involved with complexation reactions. By the way, what do we mean by donor-acceptor reaction or mechanism? Generally, a complexation, or as a general rule, complexation reactions happen between a substrate and a ligand. The substrate is the acceptor, the ligand is the donor. As you see in this demonstration here, this is the ligand and this is the substrate, and we have a binding site between them. So we can again define the concept of complexation as a covalent or non-covalent interaction between two or more compounds that are capable of independent existence. Usually, because the terminology of complexation can be like demonstrated or defined or thought of in different ways, but generally complexes are easier to separate than, let's say, a product of a normal reaction. So ligands are the molecules that interact with the substrate to form the complex. Now, this line is really important. Once complexation occurs, the physical and chemical properties of the complexing species will be changed or altered. Why this is important? Because let's say we have something and we don't like a property of this thing, or we want to change this thing to be in a way that we intend it to be, or we want it to be. So complexation is one of the techniques or methods that we can employ to change the physical and chemical properties of species or chemical entities. Like in these points, if you look over here, it says, for example, solubility, stability, partitioning, absorption, and etc. can be changed or altered if you make a complex of something. And these complexes can be beneficial in many ways, and they can be like disadvantageous or like not beneficial in other ways. So in points concerning like solubility and stability, we can improve solubility of certain drugs by complexing with them or making them complexes. We can improve stability of certain drugs or chemical entities by making them complexes. It can also affect distribution of drugs within the body, which we will talk about this one in a little bit of more detail in next slides. So now we know that complexation is just like a normal reaction that is between a ligand and a substrate, and we can alter many properties of different drugs or chemical entities by making them complexes. And we can employ this technique in a good way. So, complex stability constant. What do we mean by this one? Now, as you all know, in any reaction, from what you have heard or what you have studied before, let's say we have A plus B, we have an arrow and AB. This is the product. These are the reactants. And sometimes we have a reverse arrow, which makes this reaction reversible. So, and I'm sure all of you have heard of this thing, K, which is usually referred to as constant, or we call it reaction constant, stability constant, association constant, dissociation constant, and stuff like that. And I'm sure all of you know that this K is the representation of the tendency of these reactants to react and form this product. Now, if I ask you a very simple question, what do you think if you have a high K? What does it mean? Well, of course, it means these two reactants have more tendency to react to form this product. If K is low, is the exact opposite. Now, if you return to the slide, by complex stability constant, we mean K. We mean K. K for what? For a complexation reaction. This was our substrate. This was our ligand. We had a complexation reaction to form a complex. Well, again, here we have a K, or a stability or a complex stability constant, or formation constant, or KF. You can call it a bunch of or several different abbreviations or names, but here we call it in this slide a stability constant. And again, you know that if complex stability constant or formation constant is high, that means we have more product. That means this complex that is being formed is stable. That is why in this slide, or generally in complexation reactions, we call this K stability constant. Why? Because it represents the stability of this complex that is being formed here. This ligand and substrate has reacted to form this complex. So more K means this formed complex is more stable and the reaction has more tendency to go this way instead of this way. So it's like, that is why we call it stability constant, complex stability constant. Good. We can categorize complexes into these three general categories, and these categories are usually for pharmaceutical settings or applications. We can say that we have metal complexes, organic molecular complexes, and inclusion complexes. Let's talk about each of these. Metal complexes, or we can call them metal ion complexes. These complexes form between a transitional metal ion, for example, cobalt, iron, copper, nickel, zinc, and another ion, or a counter ion, or any other molecule to form a complex. So metal complexes form between a metal and an ion or another molecule. Now the ions can be one of these or any other like ligand. Here in metal ion complexes, the metal is the substrate and the ion is the ligand. This will donate electrons to this metal and makes it, or it will form a complex with the metal. That is why we call it a metal complex. The interaction between the metal and the ligand represents a Lewis acid-base reaction in which the metal ion is the Lewis acid and it combines with the ligand, or which is a Lewis base, by accepting a pair of electrons from the ligand to form coordinate covalent bond. Look over here. This is a question. What is a coordinate covalent bond? I am sure all of you know what is covalent bond. A covalent bond, we have a molecule here, one electron, another one electron. These two combine to form this, like this. This is a covalent bond. Okay? The difference between a coordinate covalent bond with a covalent bond like this is, in a coordinate covalent bond, both electrons come from one of the molecules. Like that. These two combine to form this. This is a coordinate covalent bond. This one is a normal covalent bond. So, in metal ion complexes, the bond that will form between the metal and the ion is a coordinate covalent bond. The ion is the ligand. It will donate both of its electrons to the metal, which is the substrate. Now you know what is a complex. We have three categories for different complexes, and I hope that you know what is or what are metal complexes. A few simple terminologies here. It says the number of ligands that can bond with the metal ion is defined as the coordination number. So if I ask you what is coordination number, you can tell me that coordination number is a property of the substrate or the metal in a metal ion complex, which defines, or which is the number of ligands that can bind with it. And it also defines the geometry of the complex that will be formed. For example, here we have a metal ion which is combined with two ligands. So the coordination number of this metal, which is the substrate, is 2 because it's able to form bonds with two ligands. Here, this metal, the coordination number is 4, Why? Because it has the ability to form 4 bonds with 4 ligands. This metal over here, coordination number is how much? 1, 2, 3, 4, 5, 6. And this coordination number also can define the geometry of the complex that will be formed, which is an obvious point to consider. So now you have to know that coordination number is a property of the substrate. In a metal ion complex, what is the substrate? The metal ion. Good. This was a property of the substrate. We have a property for the ligand as well. Let's read this paragraph. Compound, an example of a compound like NH3 has a single pair of electrons for bonding with the metal ion. So it is called a unidentate ligand. So the thing that donates a pair of electrons makes it obvious that this thing is a ligand. Okay, in this complex. If a ligand has only a pair of electrons to donate to make a bond with a metal or to make a complex with a metal, we call this ligand a unidentate. And you know this uni, I'm sure you know what uni means. It means one. If the ligand has more than one pair of electrons, let's say it has 2, we call this ligand a bidentate. Okay? If it has 3 binding sites or 3 pair of electrons to donate and to make bonds with the metal, so we call this ligand